Engineers, scientists, mathematicians, they all have one thing in common, and that is that they want to come up with optimal solutions for particular problems that they're facing. In other words, they want to minimize or maximize, right, based on the constraints that they're given for their problem. And we do this all the time. This is actually one of the most common applications of derivatives. So it's be able to find when is whatever function I'm trying to minimize or maximize, when will it achieve that minimum or maximum. So you can imagine when will in video game design, when will this character be maxed out in hit points or minimize its damage loss? In manufacturing, when will I be able to create the maximum volume for this minimal amount of stuff that I'm using to build this box? That sort of thing. So in order to optimize, we're going to need to have a constraint. So it's typically some kind of limiting factor that we're not going to be able to avoid. And as a matter of fact, it's those limitations that cause it so that you could have a minimum and maximum. Because otherwise, you could just kind of say, oh, I'll keep going forever and I'll achieve a maximum. So you have to have constraints. So you're looking for something that relates to your variables that will restrict what you're allowed to do. And then, of course, the objective function is what you're trying to minimize or maximize, and that will be some function like volume or area or hit points or whatever. You'll have to come up with something based on the variables in the problem. All right, this leads us to the maximization procedure down here. So given some objective function subject to a constraint, what's the maximum or minimum? So the first mission you're going to have is you're going to read the problem carefully, identify your variables, usually use letters that are suited to the situation, and organize the given information with a diagram or picture if possible. Then you're going to write your objective function. Your objective function is the thing that you're trying to optimize in terms of those variables. So this will be the thing you're trying to min or max, right? Minimize or maximize. All right, then you'll have your constraint functions. So you're going to identify constraints. They won't always be functions, but they're going to be limitations on what you can do. So you want to look for your limitations, and again, also write those in terms of the same variables that you already chose for step one. Then you're going to use the constraints to eliminate all but one independent variable of the objective function, and you're going to write your objective function as a single variable entity. So you can't have more than one variable. It has to be only one variable. Then you're going to find the interval of interest that affects that variable. So that'll give you your effective domain. So your effective domain is based off of whatever variable you chose for your objective function in step 4. So this will be, it's right here. So find your effective domain. So it'll be for that variable. For whatever variable you chose right here, that'll be your effective domain. Then you're going to find the, sorry about this, this will be the first order, I'll fix that for future, but it's the first order critical values for the objective function. And that's the first derivative, right? So you're going to find your first derivative and your first order critical values, so your first derivative critical values. And then you're going to use methods of calculus to find the absolute maximum or minimum. So methods of calculus is a little bit vague. Let me talk about what the 3 possibilities are. And this was actually supposed to be on the next page, so I'm just going to get rid of that. That's a typo. Okay, so what are the methods of calculus? The number one that we use the most is actually the second derivative test. You use it because, well, let me put it this way. You use it if your second derivative is easy to find, right? So use if you're looking at an open interval, a comma b, and your second derivative is easy to find. Right? The second most common one is actually the absolute max-min method that we learned about, absolute min method. That method we learned about, I think, in section 4.3. So that's you use if you have a closed interval. A comma b, right, in brackets. That's closed, not dosed. Hold on one second, let me pause and clean that up. And I mean these for the domain, right? So for that effective domain, if your effective domain is an open interval, if your effective domain is a closed interval, that's what I'm talking about right there. So if it's a closed interval for your effective domain, in other words, it has endpoints that you can actually achieve, then you're better off with the absolute min-max method, if it's reasonable, which is not always reasonable. And then the last one, the one I use the least often by far, is the first derivative test. The first derivative test is more of a pain to use because you have to make the table and all that jazz. But if you can use it if you have an open interval for your effective domain and your first derivative is a pain to find. So open interval a comma b in parentheses and second derivative is difficult, hard to find. Right? So you can sometimes tell because you've found enough derivatives at this point that, if it's a polynomial, then it's no problem to find a second derivative. But if it's something really ugly, you probably don't want to find the second derivative, right? And so then that effective domain is an open interval. So I actually put these in the order of the way that we use them. We use the second derivative by far the most often, then the absolute max-min method, especially if there's a closed interval, and then the first derivative test is the one we use the least, at least in a Calc 1 context. I mean, that might change based on what course you're in, but for us, this is the order we go in for our methods of calculus. Okay, so let's do a problem. And then we'll kind of understand, hopefully, how this all works. So we have a pair of positive real numbers has a product of 9, where x is one of the numbers. Find the x value when the sum of the numbers has a minimum value by hand using calculus. Okay, so my first mission, step 1, is to find the variables. There's no diagrams on this one, so it says skip step 1, but I'm not going to. I'm actually just going to label my variables. So my variables are x and y. There they are. I mean, you can name them whatever you want, but I said x had to be one of them, so y just makes sense for the second one. Now I tend to put 1, 3, and 5 over here and 2, 4, 6 over here. You'll see why as we go. But 1, 3, and 5 are kind of like extra work on the side, and then 2 and 4 and 6 are where the main work is being done. So 2 is the objective function. So it's the thing you're trying to minimize or maximize. So if we read through the problem again, it says a pair of positive real numbers has a product of 9, where x is one of the numbers. Find the x value when the sum of the numbers has a minimum. Okay, sum is x plus y. Now this is a new notation. We haven't seen this really before for the most part. But what it means is that this function is of 2 variables. So I have 2 independent variables right now. And I don't want 2 independent variables, but that's what I have, right? At least not in Calc 1. So that's my objective function. And capital S stands for sum, right? So that's why it's capital S. So this is sum. If I was doing product, say, I would make it capital P, right? That kind of thing. All right, so I have my objective function. Wonderful. Now I need my constraints. So that's step 3 over here. I need to constrain myself because I'm not just allowed to, pick any numbers, because if I would, I'd pick infinity and infinity plus 1, right? Everybody knows. All right, so I need some constraints. Okay, so what are my constraints? Well, it says they have a product of 9. See, that's a constraint. So that means that the product is 9, and that's x times y is 9. Oops, sorry, my dog is barking. 1 second. So we want to use this constraint to modify this function. And what we can do is we can solve it, say, for one of the variables. So I'm going to solve it for y. Y would be 9 divided by x. And then I can use that over here in this objective function. As a matter of fact, that's step 4. Step 4 is to use your constraints. In our case, we only had 1, but if you have more than 1, then use them both, to, or all of them, get only 1 variable. I should say independent variable, right? Because s is still a variable. It's the dependent variable. So 1 independent variable as opposed to 2, which were x and y. Okay. So I'm going to take my s of x, y, and I'm going to turn it into a function that's just x. Because I have the x plus, and instead of y, I'm going to write 9 over x. I now have a function that was s of xy, 2 independent variables, and now is just s of x, 1 independent variable. And just for our own benefit, we know we're going to have to take the derivative of this eventually. So I'm going to rewrite this as 9x to the negative 1. Or if you will, there, that's the part that was the substitution. All right, now step 5 is the affective domain. So I want to look at what's left, which is just x, and I want to create a domain for that. Now this particular one is actually quite easy because it says right at the very beginning, it's a pair of positive real numbers right there. So that's actually giving us our domain on this one. Now, if it said any real numbers, that would be negative infinity to infinity, but for us, this says it's positive, so we're only going to look from 0 to infinity. And it's an open bracket, of course, because you can't actually have 0. 0 is not a positive number. And it wouldn't give you a sum anyway. All right, so then step 5 is done. Step 6, we're going to find the first derivative and first order critical values. Okay, so the first derivative would be s prime of x. So s prime of x would be, the derivative of x is 1 minus 9x to the negative 2, which would be 1 take away 9 over x squared. Either one of these is fine. However, I recognize that I need to find the critical values, right? So the critical values are going to be, I'm going to set the derivative equal to 0 or the derivative does not exist. So I'm going to have to simplify this in order to get a better view. So what I'm going to do is I'm going to multiply this particular 1, and I'm going to multiply by x squared over x squared. That would make it so that it's x squared minus 9 all over x squared. That would be s prime. Now how has that helped me? Well, for the critical values, that would be, let's see, the crit values will happen when s prime equals 0 or s prime does not exist. S prime equals 0 will happen when the numerator equals 0. So that's x squared minus 9 equals 0. S prime does not exist will happen when x squared equals 0. The denominator equals 0. Oh, sorry. So this would be x squared equals 9. That'll be x equals plus or minus the square root of 9, which means x equals plus or minus 3. And this would be that x is the square root of 0, which is 0. Now, I say that, however, we actually have to knock off a couple of these. They're not going to do us any good. So x equals 0 and x equals negative 3 are not in the domain. So they're not in the domain. So only x equals 3 is a crit value for our particular purposes. So there we go. I found the derivative and I found the critical value. In this case, there was only 1. Now, this part up here, I only did this whole simplification thing. I mean, the derivative is fine right here, but I did the simplification by multiplying by x squared over x squared in order to make it so that I could find the critical values more easily. It just occurred to me you might want to see the math for how that works. So it's x squared over x squared minus 9 over x squared. That's x squared minus 9 over x squared. Okay, so we're all done except for step 7. Step 7 is we have to use a method of calculus. So in this case, because our affective domain is an open interval and our second derivative is easy to find, we're actually going to use the second derivative test. So I'm going to say use calculus method to prove min-max. Let me just put it that way, to prove min-max. And you have to use the one that's most appropriate. In our case, in this particular example, it would be the second derivative method. So we're going to use the second derivative method because we're looking at a open interval and an easy second derivative to find. So that's why we're doing that one. Okay, so what is S double prime? Since I said it's so easy to find, that means it must be. So the derivative of 1 is 0, so that's out. And then bring the negative 2 down. So that's positive 18 x to the negative 1. Oh, excuse me, x to the negative 3. We're subtracting 1. Sorry, I got distracted there. So that's 18 over x cubed. That is the second derivative. All right, so then what you do is you substitute in your value. So you found your second derivative right there. Then you sub in your critical value right here. So second derivative's right there. Right, second derivative, sub in the critical value. So I'm going to take s double prime of 3. That's the only critical value I have. And that's 18 over 3 cubed, which is 18 over 27. And I don't really actually care what number it is. What I care is that it's positive. That means that the graph is concave up at that value. And that means that I have a minimum, right, because it's concave up. So that means that the function, the sum, which is s of x, has a minimum at x equals 3. Now, they didn't ask us what that minimum was. We've actually just proven that it did. So x equals 3 is a minimum right there. We just proved it. Now, if they ask for, let's make a little note, if they ask for the y or the sum, you can find it. So if problem asks for y or sum, you use the x equals 3 and go back either to step 3 or step 4. To step 3 or step 4. Okay, so real quickly, step 3 would get us the y value. So step 3 would get us y equals 9 over 3, which is 3. So then I would know that y equals 3, right? So that's step 3. Back to step 3. And then step 4 would get me the sum, right? Step 4 would get me that the sum is x, so 3 plus 9 over 3, which is 3 plus 3, which is 6. Right there. So they didn't ask for those particular values in this problem, but they easily could have. So if they do ask for more values, you have to go back either to your constraint, which is right here, your constraint right there, to figure out your y, or you can go back to this step 4 right here when you had it limited to one variable, substitute your variable back in, your critical value back in, and you'll know what your sum, your product, whatever it is you're trying to minimize and maximize, your objective function, I should say, what your objective function would be at that value.